So we're asked to use a Ruth table to determine if the following system has any poles on the right-hand side of the imaginary axis, and if there are, how many. So, first thing we need to do is set up our Ruth table. If we look at the denominator here, the highest power of s we have is s to the power of 5. So when we set it up, we need a row for each power of s below that, down to s to the power of 0. Alright, now we just need to set up the columns, and we can go through and start to fill some things in. So the coefficient for the highest power of s is going to be a 3, so that goes in here. We have an s to the 4 term, its coefficient is 2, so that goes here. We have an s to the 3, it's going to be a 6, that goes here. S to the 2, the coefficient in front here is like a 1, so that goes there. We've then got a 5 for the s term, We don't have a constant, so that means its coefficient would be 0, and if we wanted to, every single one after this would end up being 0 as well. Alright, so now we just need to go through and fill out this first column. What we're looking for is any sign changes which occur, because that's going to indicate that there is a pole on the right-hand side of the imaginary axis. So let's start with this cell here. I'm going to give it a little, call it A for now, and we should be able to go through and solve for it quite easily. So it's the negative of the determinant of the 2 elements in the first column above it, and then the 2 elements to the right of the one we're interested in, which is 6 and 1. We need to divide it by the pivot element, which is going to be the 2. Remember that the pivot element is the one in the first column for the row above what you're interested in. So for this whole row, the pivot element is going to be 2. So if we go through and evaluate what this is equal to, it comes out to 4.5. So we can pop that in here. Alright, so to go down to this one, we're going to need to first work out what's in this cell. So let's call this B. And again, we'll pre-work it over at the side. So we need the 2 elements in the first column above, 3 and 2, and then the ones to the right, which is going to be 5 and 0. And we need to divide by the pivot element, which is going to be 2. So again, if you put this in a calculator, the determinant, these 2 times these 2, so 3 times 0 minus 5 times 2, divided by 2, comes out to 5. We can put that in here. Alright, so let's go for this one now. Call it C. Alright, so it is the negative of the 2 above, which is 2 and 4.5, and then the 2 in the right of it. And we need to divide by the pivot element, which is the first one in the row above, which is 4.5. Again, if we evaluate what this is, it comes to negative 1.222 approximately. So that's what goes in here. Alright, now to be able to get this one down here, again we're trying to fill out this first column, we need to work out what is in this cell first. So this one's quite easy. Remember, all these are basically just going to come out to zeros because they get carried down. So 0, this one here, it's got 2 zeros for the determinant. So this one here, again, if you work out what's going on, it's going to be the determinant of these 2 and these 2. When you have 2 zeros on the right-hand side here, it means that your element is always going to work out to 0 as well. So you can keep carrying these down. Again, this has got 2 zeros out here. So we're up to this one, D. So it's going to be the negative of 4.5 and 1.222. And then to the right is 5 and 0. Divide by the pivot element, which is the 222. Should have been negative in here as well. So when we work out that, it comes to be 5. Okay. So one left in here. Let's call it E. Do it here. Oh, this one's going to be easy. Again, we've got the 2 on the right hand side. So when you perform the determinant, it comes out to 0. So that's going to be 0 as well. Now, we've actually come across a special case here, because when we get a 0 in this left-hand column, what we need to do is cross it out and replace it with a very small constant, which we're calling epsilon. Okay? So it's an extremely small positive constant. And that's just going to help us with figuring out the sign changes. Because obviously if something is 0, it's not positive or negative, so it's a bit difficult. And if this had have happened further up in our column, then we would have left it as this epsilon thing, and we would have carried down epsilon just as if it was an extremely small positive constant. Alright, so we've filled out our Ruth table. What we need to do now is figure out how many sign changes we have in the first column. So, starting out here, we've got a positive value. The next one we move to is positive as well, so that's not a sign change, that's fine. Again, we go on. Here it's positive again, no sign change, so it doesn't count. Here though, we're going to get one, so it's going from positive 4.5 to negative 1.22, so there is one sign change here that we need to think about. From here, it goes from negative 1.222 to positive 5, so we've gone from negative to positive. That means there's one more sign change that we've seen. And then from 5 to this epsilon, which we're saying is an extremely small positive constant. If it's positive, 5 is positive, they're the same, so there's no sign change here. So the conclusion that we can make is that we have 2 sign changes in the first column. So this means that we have 2 poles on the right-hand side of the imaginary axis, and of course that's where we don't want them. Okay, so just as a reminder, if this is the imaginary, this is the real, we don't want poles in this section because that's where it goes unstable. So we have 2 poles in this area. That means that if we were to use this in a control system, we'd end up inevitably with it being unstable. So this is the conclusion for our question. However, what we could do is, if you have access to MATLAB, you can actually go through and check where the poles lie, because this Ruth table is only going to tell you how many are sitting in that positive real axis section. So if you go and do that, I just use MATLAB, we end up with these 5 poles coming out. We decided that 2 of them sat in the section where we didn't want them to be. So if we just quickly, I labeled these the wrong way. This is the real, this is the imaginary. So if we quickly mark these in, we have a pole at 0, so that's here. We have 2 conjugates with here and here of negative 1.61, this is 1.13 and negative 1.13. And then we have 2 others which are sitting at 0.27 and 0.97, something like this. Yep. Okay, so the ones that are causing the issue are these 2 here. Okay, these are the poles that we identified as being in the left hand side. Okay, so I guess that definitely confirms our findings from the Ruth table. In reality, you know, these 2 poles are the ones that are causing us issues. So that's all there is.